today we're going to learn about solving second order differential equations using separation of variables. So let us remind ourselves about solving differential equations. So let's take an example of having a second order equation like this, how we would solve it. So for this equation, all the typical solutions of y will be equal to exponential function rt, where the first derivative of this function will be r, exponential function rt, and the second derivative will be equal to r squared e rt. When we punch these into this equation, we'll come up with r squared exponential function rt plus r e rt plus exponential function rt is equal to 0. When we factor out the exponential function rt, we remain with r squared r plus 1 equal to 0. When you divide through by the exponential function, you come up with r squared plus r plus 1 is equal to 0. Now when you look at this, we have a quadratic equation. It can either be solved by factoring or by using a quadratic way of solving, where r is equal to negative b plus minus the subscript b squared minus 4ac over 2a. Now, as if we have case 1, finding the solution to this, if we have our case 1, solving this equation, we shall have the subscript, in the case 1, the subscript b squared minus 4a squared ac will be greater than 0. For these kinds of equations where the subscript is greater than 0, it is known to be a hyperbolic equation. Now, for where this subscript is greater than 0, we'll have our general solution of the hyperbolic equation having two real roots. For that to be true, the two real roots, the equation will be y, the function, the general solution will be y, constant x, exponent function r, x, r1, since there are two real roots, plus c2 e r2 x. This will be our general solution, because in this case where the hyperbolic equation, its subscript is greater than 0, we have two real roots. Then in case 2, where the subscript b squared minus 4ac is equal to 0, in this case we're dealing with parabolic equations. Now for parabolic equations, we have two repeated roots. Repeated roots simply means you have r1 and r2 being the same, maybe 1, maybe 2, maybe 3, but they're same. Okay, for this case, the general solution will be c1 exponential function rx plus constant 2 x exponential function Rx. Okay, this will be our general solution where we're dealing with a subscript that is equal to 0. Now for case 3, where our subscript b squared minus 4ac is less than 0, in this case we're dealing with elliptic equations, our roots will be complex. In this case, our general solution will be e alpha x into the first constant c1 cos beta x plus our second constant c2 sine beta x. That will be our general solution. Okay, now an example of real roots can be r1 could be r plus beta complex, or r2 could be r minus beta I. So I hope we've gotten this, because it's very fundamental in solving our PDs. I just needed to introduce this before we could solve for this quadratic equation. So let us proceed and solve for this example one that we're using, as we're reminding ourselves. In this case, our A is 1, our B is 1, our C is 1. So R is equal to -1 plus minus 1 squared minus 1 times 1 over 2 times 1. In this case, we have -1 plus minus 1 minus 4 over 2. So in this case, we have a complex solution, which is -1 plus minus square root of 3 complex over 2. So we have two complex solutions. In other words, the function y is going to be equal to e. Our first complex solution is alpha. Alpha will be -1 plus square root of 3 complex divided by 2 x into our first constant cos beta will be -1 minus square root of 3 complex divided by 2 x plus c2 sine x. This will be our general solution. Now, if we have a quadratic equation of our DE, if we have our DE that gives us two real roots, we'll write the general solution in terms of the in terms of real root general solution. If it gives us 2 repeated roots, we'll write the general solution in terms of the 2 repeated roots general solution. Okay, so let us deal with now. Let us find out how to solve 2-order partial differential equations. This was just a reminder about how to solve PDE differential equations, which we are going to use in solving our 2-order, second order partial differential equations. So let's have an example 2, where we find the general solution of variables using separation of variables. Now, for this question, our function, in this case, our general solution to this question will be the function of x with respect to x, and y functions will be equal to the function of x with respect to x times the function of y with respect to y. This is what we are looking for. It's the solution to this problem. It's a general solution to this. Okay. So, what would be the partial differential of the function u with respect to x? It will be the first derivative of function x times the y constant. How about the second derivative of the function with respect to x? It will be x double prime y. It remains constant because it's with respect to x. Then how about the partial derivative of the function x with respect to y? It will be x is constant, y prime. Okay? So we just get these and punch them inside this equation. We'll come up with, this is here, x prime prime y minus 2 x exponent y plus x y exponent equal to 0. Now we separate the variables. We put the y's on the other side, the x's on this side. We'll come up with x double prime minus 2x prime y is equal to x y prime. Okay, when we separate x to bring it to this side and y to the other side, we come up with x double prime minus 2x over x is equal to y prime over y. Now, for this expression to be true, all this is a function of x and all this is a function of y. So for them to be equal, they can only be equal if they're equal to a what? A constant, lambda. Let's never forget this. So we are now going to form a quadratic equation. X, we'll make an equation with the x's alone. X, and it comes up with 2x exponent is equal to lambda x. So in this case, to solve this, remember what we talked about. The typical solution of this will be x being equal to ERT, where x, differentiating this will be ERXT, and the double prime will be R squared ERT. So when you put this into this equation, it will be R squared ERT minus 2R ERT minus lambda ERT is equal to 0. When you factor out the exponential function, you come up with, when you factor out the exponential function, you come up with R squared minus 2R minus lambda is equal to 0. It's a quadratic equation. To solve this quadratic equation, remember the value of R is equal to minus B plus minus B squared minus 4AC over 2A. In this case, our A is 1, our B is negative 2, our C is negative lambda. So our R is equal to 2 plus minus square root of 4 minus 4 times negative lambda over 2. In this case, it will be 2 plus minus, okay, let's first convert that, 4 plus 4 lambda over 2. In this case, we'll have R is equal to 2 plus minus, we'll factor out the 4, it will be 2 over 1 plus lambda over 2. When you solve this, our R is equal to 1 plus minus 1 plus lambda. So R1 could be equal to 1 plus 1 lambda square root, or equal to 1 minus 1 minus plus lambda square root. Now, because this is a constant, it means that our roots could be either complex, or it could be 2 repeated roots, or it could be real. So let's assume the function, when you put in the value of R, it gives you real roots. If the roots are real, it means we're going to use the other function of real roots. The general solution gives us the function of x when its real roots is a constant 1, e r1, which is 1 plus square root of 1 plus lambda, x plus constant c2, the exponential function 1 minus 1 plus square root, okay, x. This is our general function of x. Okay, now how about y? Remember that we had our y, when we remember what we wrote earlier on. Sorry, the board is small, I couldn't put everything here. So the other function of y was like this, is equal to a constant. We multiply through by the negative, it will become y complement over y is equal to negative lambda. Now, when it's only one, it differentiated one, so it's very easy, you just integrate. When you integrate on both sides with respect to y, it will give us ln of a function y is equal to negative lambda y plus a constant c. When we want to remove this, remember we want a function y, so we remove the natural log. It will be function of y is equal to a certain constant a times the exponential function of lambda y. Okay, where the a is EC, exponential function of the constant, which is a constant. So we now punch this. Remember our general solution, xy is x function of x with respect to x by the function of y with respect to y, which is with this is here and this is here and this is here. So we just multiply them. The general solution is equal to C1e 1 plus root of 1 plus lambda x plus C2e 1 minus root of 1 plus lambda x. This is our x function times the y function, which is a okay. So when we multiply through, we'll get b e 1 plus root of 1 plus lambda x minus lambda y plus d e exponent the function 1 minus root of 1 plus lambda x minus lambda y, where b is c1 times a and d is c2 times a. So this is the general solution. This right here is our answer of the general solution. Now, if they had given us boundary conditions or initial conditions, we would have just punched in and we would have been able to find the value of b, d, and even the lambda. Okay? So in the practice equations that I'm going to give you, we'll have these defined. We'll have conditions where you just punch in and you find a particular solution after punching in and getting to find the unknowns b, d, and the lambda. Okay?